Welcome everyone to the third video of the DP-900 Data Fundamentals course. And today we are going to dive a little bit more into databases, specifically OLTP and OLAP solutions. Yet last time, I almost said yesterday, last time in the last video, we talked about some possible Azure solutions that you could use. For example, Azure SQL or open source relational databases for Azure or Cosmos DB. We'll talk about the specific applications of those later. Before we get into talking about specific products, let's just take a very broad overview of the concept of a database and yeah, just basically some important ideas and maybe even some history of databases. Again, we'll go back to the history. And once again, I acknowledge that this is probably not the most exciting YouTube series for you to watch. So please watch this at 1.5 speed, take breaks every now and then, pause, basically treat this like a lecture. And as always, if you have any questions at all about the material I'm presenting, consult the slides that I've made available on Canvas, send me a message on Slack, do whatever you have to do, and use Google. Yeah, so just a rehash of what we're going to go over. Once again, this is the first, oh, and also pardon the echo, everyone. I'm in a very echoey room right now. But here is an image of the first visualized black hole, I believe. Really, really cool story. It was I believe NumPy has a case study on it. In fact, it definitely does. Definitely encourage you to check it out, and just so that you could see some other applications of computing to help make scientific breakthroughs like these. Super, super cool stuff. All right, so before we get into any new content, let's do a little bit of review. And I might ask you these questions during class time as well. I want you to consider these three questions, pause the video, try to answer them yourself, and yeah, then maybe we'll go over the answers together. So question number one, what are the three structure categories of data? Or another way to phrase this, what are the three categories of structures of data? Question two, which database solution is a non-relational database system that allows you to store JSON, key value pairs, column families, and graphs? Specifically, which Azure database solution? And finally, which open source Azure database supports hybrid relational object operations? Pause the video, see if you can answer those based on off what you watched, what you learned from the past two videos. Okay. So for question one, that is structured, semi-structured, and unstructured. Let me just write that down for structured, semi-structured, and unstructured. Question two, which non-relational database system in Azure can you use to store this type of data? Well, that is Cosmos DB. We'll learn about the API later. And finally, which open source Azure database allows support, for hybrid relational object operations? Well, that's good old PostgreSQL. All right. We'll skip this since we didn't talk about these solutions yet. Let's dive into the concept of databases. So once again, if I haven't impressed this idea upon you enough, databases are honestly one of the most important progressions in the history of technology, more than LLMs, maybe. We'll see how that pans out. Definitely more than NFTs, definitely more than, yeah, just the very, very important part of computation history. And without databases, we wouldn't be where we are at now. All right, so a couple of discussion questions, and you don't really have to, there is no right or wrong. Well, actually, there is a right answer to this, but, we're not going to, Azure's not going to ask you on this. DP-900 is not going to ask you. This is just for you to consider yourself. What kind of databases have we used during the Innovation Fellowship? And what is the difference between a database and a file system? Think about those questions, and then we'll move forward. All right. So a database, everyone, is a central system for storing and querying data. In the most simple terms, if we just boil down databases to their most essential components, databases should allow massive storage of massive amounts of data, access via a query language, durability, even during power failures, and finally, the ability for multiple users to interact with the data without stepping on each other's toes, right? And you'll see what I mean when we go over the ACID components of a database. But yeah, this right here is the de facto system of storing data. And there's a reason for that. What happens when we don't listen to good ideas? Well, we unfortunately use the wrong tool. And when we use the wrong tool, systems fail for one reason or another. An example was back in 2020 when the UK Health Ministry was doing contact tracing, and they stored their data in Microsoft Excel 2011 edition, I believe. And I think, if I'm getting the story correct, is Excel had a row limit of 65,000, and they were putting a lot more than 65,000 rows into one file. And what happened is that Excel would just basically cut off the rest of the data. So essentially, the UK Health Ministry experienced data loss due to the system that they were using. And this is why it's very important to not just be a user of the product, but also someone that can decide which product is appropriate and which product is not, right? You don't want to just like take an out of the box solution and be like, well, you know, I used this for my last job, so why not use it again, right? No, you should really consider the pros and cons. What risks are you accepting, or what risks might you encounter, or normal disasters? If you ever read Norman Thoreau, what normal disasters would you accept, or normal accidents, I believe they call it, would you accept by using this system? And unfortunately, with the usage of Excel, they did not report 15,800 positive COVID cases. And this occurred from September 25th to October 2nd. And I believe at the end of the day, they were able to get the data back. But just goes to show, databases must be able to store massive amounts of data. If you have a cutoff for your database, or what you're treating as your database, you should be very, very aware, or not just very aware, you just should be aware about that limit. All right, so now that we understand what the core components of a database are, let's talk about two broad categories of databases. The type of database that you all learned about, relational databases, that's when we have relations or tables and they're connected with a variety of relationships. And then we have non-relational databases. And that's where we implement what we call NoSQL solutions. And NoSQL does not mean like NoSQL, like SQL is not permitted. It basically means not only SQL. The SQL API is supported in NoSQL solutions, but the way that we store data is a little bit different than the relational structure. And you'll see what we're talking about when we get into these databases. So first up, everyone, is the relational database. This is just a review of PostgreSQL, or just relational databases that you've been using throughout the Innovation Fellowship. Data is stored in tables, also known as relations, just for note-taking purposes. If you ever hear the term relations, it's just a table when we're talking about databases. So yeah, data is stored in a table, and each row essentially represents an entity or an event, or just basically some discrete object or thing that we're trying to record. Maybe it's a customer. Maybe it's an item that's available for purchase. Maybe it's a weather event, something along those lines. And each of these rows should be assigned some sort of key that uniquely identifies, right? Basically, we want to do something called data normalization, which we'll talk about in the upcoming slides or lectures. And abiding by this data normalization, specifically 3NF or third normal form, once again, we'll talk about that later, we are able to store data only once. And I want you to think about it. Why is it important to only store data once, right? What is the risk that you accept when you have the same piece of information stored in multiple locations? For example, and this is going to be ridiculous. All my examples are ridiculous, but hopefully they, get you thinking a little bit. Let's say you have a file cabinet and you are, storing information on your budget within this file cabinet. Every single week, you plan out your expenses, you write them out, and you just basically have a file cabinet of your expenses. Now, let's say 1 week you make two versions of the same budget, but you record different information in those two pieces of paper. Which one do you believe, right? If you were to go back in history, or let's say even if you were in more serious terms, auditing a company, or you were getting audited, hopefully not, and they took a look at these two pieces of paper, well, what do, right? Do we combine the information? Do we throw out one piece of information and keep the other? And if we do, which one do we keep? That's a really tough problem. And by guaranteeing that we only store information once, we don't run into this problem. We have good data integrity, is what we call it. Anyways, let's keep moving forward. Tables and data in the tables are managed via SQL or updated and queried via SQL, the structured query language. And at this point, SQL is actually standardized by the American National Standards Institute. So basically, any flavor of SQL that you use, the core components are mostly going to be the same. There's going to be some changes that you should be mindful of, but all in all, almost all flavors of SQL are going to behave the same way. All right, next up, we have non-relational databases. So first was relational databases, which is your table data, data and tables, and then you have your non-relational databases. Now, I'm sure there are more types of non-relational data, and that just basically means like non-table data. But essentially what it means often, or what it could mean, or it could signify, especially in the context of Azure and Cosmos DB, is when we have non-relational data, which includes key value databases, document databases, column family databases, and finally, graph databases. Sometimes the data that's stored in non-relational databases is semi-structured. I should probably update this slide. And sometimes it does not contain a schema. Maybe there's not a strict format that the data has to absolutely abide by. Maybe it's a little bit more flexible. But yeah, these are the four common types, especially that we'll see in using the Azure suite of tools. Now, let's actually dive into, pardon the brief cut, everyone. My internet went out. So hopefully if I do a good enough job editing these two videos, I'll be able to seamlessly merge them together. You won't even know that anything changed. But anyways, let's dive into the concepts or some types of non-relational databases, starting with key value stores. Now, essentially, a key value store is very similar to a relational database, except instead of keeping track of the relationships between tables and tracking multiple columns and different entities and events, we simply store two things: a key and a value. The secret is in the name. The key is a unique identifier that we can use to identify some value, and a value could just be a simple object. For example, here we just have some binary data. This is good for temporary storage of simple objects, such as a web cache. Now, the next type of non-relational database is a document database, and often this is the first type of NoSQL solution that people are introduced to, for example, in MongoDB. And in here, we store a collection of documents, and we retrieve these documents via, once again, unique keys. Now, the type of object that we store is called a document. However, they are commonly and most often a semi-structured format, such as a JSON object. And this is great for handling large volumes of semi-structured data. And going back to that Amazon example where you have an item in your shopping cart that may or may not be ordered, maybe this is something that we could potentially use due to the different attributes that we have to keep track of for this object. And if you take a look at this example here, you'll notice that the schema isn't necessarily fixed, hence why we call this semi-structured. Next up, everyone, we have the column family non-relational databases. And once again, we are storing data in rows and columns, just like for relational data. However, the structure is highly denormalized, and we denormalize the structure in order to model sparse data. We divide columns into groups known as column families. And as you'll see, when we get into more normalization concepts, this is usually a huge violation of normalization, but this is done purposefully in this non-relational database in order to store very specific type of data. For example, notice that here we have a column family called identity, and identity could have different attributes inside of each row. Some attributes are shared, some attributes are not. For example, here we have first name, last name, suffix, title. Not every row is going to have suffix or title, so on and so forth. And last but not least, everyone, we have graph databases. We really didn't talk too much about what a graph is during the Innovation Fellowship. I might bring it up for fun during class because it is a pretty cool type for abstract data type. And it's really, really good for understanding different types of relationships. And basically what we do in a graph database is we store data in nodes and edges. Nodes are objects and they represent discrete, maybe entities, and edges are the relationships between these objects. And graph databases are pretty good for storing relational or relationship-based queries. For example, who reports to whom in this organization? A graph database might be appropriate for solving this problem. All right, I'm going to skip these review questions, and let's now that we've talked about the different types, and pardon me, now that we've defined relational and non-relational databases, let's talk about another broad category of databases, which is OLTP databases, also known as online transactional processing databases, and online analytical processing databases. So let's go ahead and skip these discussion questions and let's dive into the history of databases once more before we formally identify OLTP databases again, or formally identify OLTP databases for the first time. So by the 1990s, OLTP databases or transactional databases were pretty ubiquitous in commerce and many types of different enterprises. However, they realized that if they want to do analytics, for example, just summary statistics or descriptive statistics on sales, on who's buying the most, when are peak seasons, low seasons, OLTP databases are not very well suited for that. Instead, they needed to come up with an analytical database, which we will talk about throughout these slides. Before we get into analytical databases, let's just go ahead and talk about OLTP databases, which basically serve as the core of business operations. Essentially, everyone, OLTP databases are the primary function, just like I mentioned, of business computing. We want to record transactions, and I don't mean transactions in the financial sense where we send money, from one place to another. Rather, we're talking about specific events on the database, right? Has a new user signed up? Has this user purchased something? Has this user deleted their account? Well, all of those actions, they really should be efficiently handled using OLTP databases. And just to further define what a transaction is on a database, it's essentially a single unit of work. And when I mean a single unit of work, I want you to think back to the SQL queries that you've written. For example, select all from table where column is greater than 500. That right there is a single unit of work. That single query, that is a unit of work that needs to be performed on the database in order for you to get the information that you want. Now, it's not enough to just encapsulate a query as a transaction in name and just consider it to be a transaction. Rather, an OLTP database, and specifically a transaction, must abide by ACID semantics. And ACID is an acronym which stands for atomic, consistent, isolated, and durable. And we're going to talk about what all of these terms mean in a few examples in the upcoming slides. In fact, I'm not even going to bother talking about these definitions until you see the example that goes with these definitions, and then we'll formally define them one by one. So first up is atomic or atomicity, which is basically, and I know I just said we're not going to define it, but I will give you a little preview. The concept that all operations execute or none of them do. There is no such a thing as half operations. There's no such thing as almost completing a transaction, but then backing out halfway, and then you're just left with half a unit of work done. It's either complete or not complete. And here's an example. Let's say, and I know I just said that transactions are not related to financial transactions, but in this case, we are going to relate them to financial transactions just because the example works so well. Let's say you have two bank accounts, and you want to transfer money from one bank account into another. Now, let's say in order to perform this transaction, the customer, has to click on a certain, arrangement of buttons in order to get this going. But in the back end, we have a SQL query that's going to be performed. And we are going to call this SQL query transaction A. And this SQL query is in the first operation, going to withdraw $500. And for the second operation, it's going to deposit that $500 into bank account 2. So it's basically doing two things, right? It's subtracting $500 from bank account 1, and it's adding $500 to bank account 2. Hopefully, this concept is nice and simple, and you're comfortable with it. Let's go ahead and see what atomicity implies in this transaction. Let's say the customer clicks accept or confirm or whatever button they need to in order to start this transaction. The first transaction, in a few microseconds completes. $500 is taken away from their bank account. But then at the very instance when we're about to go into operation 2, where we deposit $500, a solar flare strikes the earth, and all financial systems and communication systems and basically anything that's operating off of electricity gets short-circuited or whatever, and systems fail essentially. Unfortunately, I'm not educated in any sort of electricity or electrical components, so I can't tell you exactly what's going to happen, but things basically fail. Now let's think about what could happen in the worst case scenario. So let's say this person, bank account one, is paying their rent, and or their share of the rent, I guess, since it's only $500, living with roommates. They spend $500, but then once the solar flare hits, all systems shut down. So what they could be left with is the fact that they just subtracted $500 from their bank account, but they didn't send $500 to the other bank account. So basically, you just wiped value off the face of the earth, which should not happen, right? That's not how financial system should work. So for that reason, atomicity says if one operation fails, if anything fails at all the operations fail. So essentially, what happens here, everyone, is basically the entire transaction does not get evaluated, does not get executed. So it's as if nothing happened at all. And that is what we call atomicity. A transaction either succeeds completely or fails completely. There are no half measures. Next up, everyone, we have consistency, which is pretty simple compared to the other example of atomicity. And this just basically says that data is valid and complete. Essentially, what it says is if a transaction fully executes, the status of the database, basically, we don't create new value and we don't delete value. The value stays consistent. $500 being sent from one place to another is just $500. We cannot only send $499. We cannot send $501. The total money that's just flowed from one bank account to another is $500. Yeah, data is consistent, valid, and accurate throughout all transactions. We do not have rounding errors. We do not have any sort of state that invalidates this data. $500 was sent, $500 was received. Nothing more, nothing less. All right, next up, everyone, we have isolation. And that's essentially the concept of not peeking at each other's transactions and basically locking transactions until one transaction is complete. And this gets into some more complex concepts of deadlock and transactions waiting upon other transactions and different kinds of reads. But basically, consider this example. Let's say, once again, we are sending money from bank account one to bank account two, but there's also another transaction that reports how much money someone has in their bank account via a bank account dashboard. And I'm sure at this point, every banking app has a bank account dashboard. That's when you log into the app and you see how much money you have in your account, right? So in order for this to happen, the dashboard needs to peek at the balance, essentially. It needs to request the balance from bank account one. Now, let's say this transaction began, transaction A, where we send $500 from one bank account to another. So we start operation one, but at the very instance when we're about to go to operation two, transaction B attempts to peek at the balance. However, because transaction A is not done yet, we basically lock it away from peeking at the balance. Essentially, we're telling transaction B, like, hey, can you please wait a little bit? We are waiting for one transaction to complete before you perform your operation. And if you think about it, this is very important, right? Because we don't want transactions happening at the very same instance on the same piece of data. Let's say transaction B was not just a peek. Let's say it was also a request for $500. Well, what could potentially happen? Maybe we'll request $500 from the same bank account source, and due to that, we'll essentially only withdraw $500 once, but $500 will be spread across two different bank accounts, even though it was only deducted once from the original bank account. And maybe that's a little bit of an extreme example, but it just basically highlights why we need to lock transactions out from manipulating the data until another transaction is done. So essentially, until we complete transaction A, transaction B is not allowed to look at the bank account balance. And this is known as isolation. Transactions cannot interfere with one another. One transaction cannot observe the intermediate state of another transaction. The only time we can interface with this bank account is when another transaction is complete, or when no transactions are performing operations, essentially. All right, and finally, everyone, we have durability. Once again, this is one of the more simple ones. It basically says after completing a transaction, and then let's say we power off the system for the day or for maintenance, our value is not going to be lost. We're not going to undo transactions, right? Basically, if a transaction completed, a transaction will stay, especially in the history of transactions. Commits stay in place, even after system failure, or even after a system shuts down purposefully. All right, so once again, everyone, these are ACID semantics, and that is atomicity, consistency, isolation, and durability. I almost forgot the C. Let me just double check. Yes, consistency. I don't know, had a little short circuit there. Anyways, this allows us to support live applications that process business data, also known as line of business applications, LOB. So OLTP solutions, everyone, once again, these are hyper-engineered systems that are designed to support the, essentially everyday operations of a complex real-world system. So now that we talked about OLTP solutions, let's talk about OLAP solutions, or online analytical processing. So I'm going to skip through these discussion questions. I'm actually going to go ahead and skip through this timeline as well. I was going to go through a little bit of a historical tangent as to like the first time OLAP research papers were published, but really just going to skip all this. And let's just dive into what an OLAP is, or an OLAP database. Essentially, an OLAP database is a read-only system. Key phrase there, read-only, no updates, that stores vast volumes of historical data or business metrics. In fact, it doesn't have to be a current or a live snapshot. It could be a snapshot that occurred in history at any given point in time, or it could even be a series of snapshots. But basically, the concept is this data is denormalized. It doesn't abide by any relational schemas, and it is essentially designed for analysis. And if you want analysis, then you need to be taking aggregates. You need to be considering different time frames, so on and so forth. All of those requirements go against normalization, go against the common format of an OLTP database. Let's dive a little bit deeper into this. Here's the common workflow of an OLAP solution, or online analytical processing solution. In fact, in the absence of text, I'm just going to go ahead and talk about this in abstract terms. In step one, we basically collect a bunch of data. We might even collect data from an OLTP source, like for example, from PostgreSQL, and then maybe from some CSV files that live in Google Drive or something along those lines. And we combine all of that data into a centralized store that could be a data lake. From the data lake, we create something called a data warehouse, which we'll go into more detail later. And then finally, after creating a data warehouse, we create something called an OLAP cube. Now, using that OLAP cube, we are able to form a dashboard or present our findings to some stakeholders or to some researchers or other important people in our team who will then act on those findings in their day-to-day operations. Like, for example, let's say we work for a certain hotel brand and it's the off season for a certain location. Well, we could collect that data based on the volume of bookings, or rather lack of volume of bookings compared to previous months, feed it through this pipeline, and eventually when we get to the dashboard, we can basically tell people or our coworkers, hey, we have less volume coming into these hotels maybe we want to scale down to food service or something along those lines. And once again, I'm no expert in hotel management. Maybe we don't want to scale back food service. That was just an abstract example. Now, let's just define some of these things that we just talked about. A data lake in Azure is a blob storage with a hierarchical namespace. And if we are basically organizing files and other pieces of data in a folder in folders on a distributed file system. And we'll get into more detail when we actually get onboarded into our Azure environment. Now, a data warehouse, and if you remember, that's actually going to be step 2 of this pipeline, is a relational data store that is optimized for read operations. And there's basically certain schemas that we can use in order to focus our queries, or basically design the tables in such a way that we can request specific analytical information on our data that was previously in a data lake. And finally, everyone, using a data warehouse, we could transform our data into something called an OLAP cube. And this is basically when we pre-aggregate our data so that we don't have to use precious computational power performing these aggregates. And this data store is optimized for what we call analytical workloads, which we then feed into something like a dashboard, or even maybe even just some slides that we are going to present to our coworkers and internal team members. But the main idea, or the main focus of an OLAP cube, is that we pre-aggregate across multiple dimensions, which allow us to make quick summary statistics. And yep, we just talked about this workflow already. I'm going to actually skip through this just because this gets into some territory that I don't think we should necessarily talk about. And we're just going to skip to readings. So here are the readings from the previous week. Hopefully, by the time you watch this video, you're familiar with all these terms, such as blob storage and different types of data services in Azure, and what is infrastructure as a service versus platform as a service versus software as a service. And then next week, everyone, we are going to talk about more relational databases. We scratched the surface of what a relational database is, along with OLTP databases. And we're really going to dive a little bit deeper into normalization, different database objects, and also likely go over some SQL syntax. All right, so that's going to be it for this video. Thank you all so much for following along, and I will see you all next week.